Welcome to Build Through Time. Today we're embarking on an incredible journey to explore one of humanity's most ambitious creations,
hmm
the International Space Station, or ISS. For nearly 25 years, this orbiting laboratory has been, well, a real beacon of international collaboration and scientific discovery. We've gathered some fascinating insights into its past, its present, and the really complex future that lies ahead for it.
It really is a unique human endeavor, isn't it? And the sheer volume of information, I mean, it's immense. We're going to examine not just the marvels of its construction and, the groundbreaking science happening up there, but also the significant challenges that NASA and its partners face in sustaining it and eventually bringing it all to a safe conclusion. You'll hear about everything from how microgravity impacts the human body sometimes in surprising ways to the very real threat of orbital debris and the intricate plans for its eventual deorbit.
Let's start with appreciating the sheer scale. I mean, this orbiting marvel wasn't built overnight, was it? Or by just one nation alone. This was a huge undertaking.
Oh, absolutely. The foundational elements, they were launched back in 1998 by NASA and Roscosmos. And since then, you've had the Canadian Space Agency, the European Space Agency, JXA, the Japan Aerospace Exploration Agency. They've all contributed parts expertise. It makes it a truly global effort. Think of it as the world's, preeminent orbiting laboratory, a massive collaborative project, constantly evolving for, over 2 decades now?
And what a lab it is. Beyond just being a symbol of unity, what's its core mission today? Let's say, specifically for NASA.
Well, it serves several critical purposes. Firstly, it's kind of a springboard for commercialization in low Earth orbit. It's actively fostering a new space economy. You're seeing companies really exploring the potential up there. Secondly, and this is perhaps most crucial for NASA, it's essential for their long-term deep space exploration goals. We're talking missions to the moon, eventually Mars. The research on the ISS helps us figure out how humans can live and work in space for extended periods. It really paves the way.
It must be an incredibly busy place then. What kind of, groundbreaking work are we talking about up there? Work that actually impacts us down here on Earth?
The range is just astonishing, really. Since 2021 alone, 684 new investigations initiated, 501 completed. These span biology, human research, tech demos, earth science, you name it. What's particularly interesting is how it's become a hub for non-NASA groups, too, through the ISS National Laboratory. That's managed by CASIS.
So it's not just government agencies doing the science. That sounds like a real democratization of space research almost.
Precisely. You've got small companies, major research institutions, Fortune 500s, even other government agencies using it. Like, for example, research on protein growth. That's been key in developing new treatments for diseases like Duchenne muscular dystrophy. We've seen studies on cancer formation, advanced disease models, even things like manufacturing human tissues in space. Just imagine the possibilities there.
That is truly impactful for life down here. Are there any examples that might surprise people? Maybe something less obviously medical?
Oh, definitely. There's Ecostrus, for instance. It collects incredibly precise data on land surface temperature. That helps us understand droughts, plant health, gives us a clearer picture of climate impacts. And in education, this is amazing. Over 2.6 million U.S. students have designed experiments launched to the ISS. Think about that scale. There was an 8th grade team recently. They sent up a test for bacterial contamination using horseshoe crab blood. Plus, the amateur radio on the ISS program, it's connected over 250,000 participants directly with astronauts. It's such a powerful inspiration for future generations, showing them space isn't just for, rocket scientists.
It really sounds like the astronauts are just constantly working. What does the typical work week even look like up there?
Yeah, forget your standard 40-hour week. Astronauts on the ISS are clocking an astonishing amount of research time. The official goal is 35 hours per week for a crew of 3, but it ramps up to 68.5 hours for 4 or 5 crew members. In fact, there was a period, October 2019 to April 2020, where they averaged nearly 120 hours per week just dedicated to research.
Wow, 120 hours.
Just research. It's truly a nonstop science factory orbiting our planet.
Okay, so from this incredible collaborative spirit and the constant science output, we have to shift focus a bit. We need to look at the challenges that come with, 2 decades in space. Because like any grand structure, even the ISS is starting to show its age. What are the most significant physical vulnerabilities? Maybe some hidden ones that come with the ISS getting older.
Right. As the station ages, NASA faces increasing risks to keeping operations going through 2030. One of the absolute top safety risks involves ongoing cracks and air leaks. These are in the Russian service module transfer tunnel. That's an area where the crew actually lives and works.
Cracks and air leaks. in space.
Boy.
That sounds like a fundamental integrity issue. What's the actual risk level here?
It is serious. Now, officials say it's not an immediate risk to the overall structure, but the leak rate increased, hitting its highest level in April 2024. It reached 3.7 pounds per day. Compare that to the planned rate of just zero point 0.6 pounds per day, so significantly higher. NASA has actually elevated this to the highest level of risk in their management system. Both NASA and Roscosmos are investigating, looking closely at internal and external welds. They're monitoring it constantly, and they close the hatch to that module when it isn't needed. But you see, a permanent closure would really impact cargo delivery and crew access. It's a tricky situation.
And beyond actual cracks, what other sort of structural or operational challenges are popping up with such an aging, complex system?
Well, yeah, beyond just structural integrity, maintaining the ISS means constant repairs, constant upgrades. And as 2030 gets closer, just acquiring key replaceable parts is getting harder. Suppliers are decreasing production or sometimes stopping altogether. They've identified 4 specific parts related to science facilities and an exercise system where there are just no available spares, no near-term availability, and no real mitigation plan if they fail. It's like needing a crucial part for your classic car, only to find out nobody makes it anymore.
And then there's the environment outside. Space isn't exactly gentle, is it? What about threats from micrometeoroids and orbital debris, MLD?
Right, MMOD. That threat is considered a top risk to crew safety, to the ISS structure itself, and even to the vehicles visiting the station. We've seen some pretty impactful events recently. Back in December 2022, a probable MMOD strike hit a docked Soyuz spacecraft, caused a coolant leak, forced them to cancel a planned spacewalk, and they needed a whole contingency plan just to get that crew home safely. Then in June 2024, a defunct Russian satellite broke apart, created hundreds of trackable pieces of debris. That forced the ISS crew to actually shelter in their return vehicles just in case.
So what does all this mean for actually protecting the station and the crew? Are they sufficiently shielded,
Right.
or is it a bit of a gamble?
Well, NASA uses shielding on the U.S. segment, but it's mainly effective for debris about 3 centimeters or smaller. For anything larger than 10 centimeters, they rely on the space surveillance network to track it and hopefully maneuver the station out of the way. But here's the critical point. They've essentially accepted some level of risk. They aren't adding more protective shielding mainly because of the high costs and technical challenges involved. The real problem is, while we track objects bigger than 10 centimeters, there's an estimated 100 million pieces of debris smaller than that, and they're untracked. These are still big enough to damage the spacecraft, or worse, puncture a spacesuit during a spacewalk. Remember that Russian anti-satellite test back in November 2021? That created over 1,500 trackable pieces, forcing the crew to take shelter then too. So these smaller, untracked pieces, they represent a significant, almost invisible safety risk. It's like a silent minefield up there.
Okay, so we've covered the structural threats, the external threats like debris.
Yeah.
But what about the most complex, maybe the most vulnerable part of this whole equation? I mean, the human body itself. What kind of toll does spending years in orbit take on our actual biology?
Yeah, this really raises a fundamental question for any long-term space mission. How do we manage the big 5 hazards in space? Those are changed gravity, cosmic radiation, isolation, the dependence on the spacecraft itself, and the sheer distance from Earth. For the body, microgravity and radiation are the main physiological factors directly challenging astronauts.
Let's start with microgravity then, that feeling of weightlessness. We've all seen astronauts floating around. It looks fun. But what does that actually do internally, say, to the heart and blood vessels?
Your body adapts pretty dramatically, but not always in a good way for returning to Earth. Astronauts experience reduced exercise tolerance. They also get something called orthostatic intolerance. That basically means they have difficulty standing upright when they get back because their blood pressure can just plummet. Their circulating blood volume decreases significantly up there. That means less blood is pumped with each heartbeat. So the heart rate increases to try and compensate. Interestingly, we actually see their resting heart rate decrease by about 20% over a 6-month mission, with most of that adaptation happening in the first month.
So the heart itself physically changes in space.
Right.
That's really profound.
Yes, they observe heart remodeling, and that can lead to issues like arrhythmias, irregular heart rhythms. Even down at the cellular level, space changes things. Studies on human stem cell-derived heart muscle cells. They show reduced calcium recycling, which impacts how they function. The good news, though, is that preventative measures like rigorous in-flight exercise and fluid resuscitation before returning, they show real promise in minimizing those post-flight blood pressure problems. But it's definitely a constant battle against the body's natural response to floating around.
And what about bones and muscles? That's probably the most common concern people think of with space travel. How significant is that loss, really?
It's one of the most researched areas, and absolutely for good reason. Microgravity leads to significant bone mineral density loss and muscle atrophy, of course. The loss is much more pronounced in the weight-bearing tissues, your legs, your spine. For instance, the Apollo 17 crew. They saw a 5–6% bone loss just in their heel bone after less than 2 weeks. And some Salyut 6 missions, longer duration, showed nearly 20% loss in some areas.
Imagine your skeleton essentially dissolving itself because it doesn't need to fight gravity. What's happened is microgravity basically signals the bones to release calcium. That, in turn, suppresses the hormones that are essential for absorbing calcium and building new bone.
So that intense exercise regime must be absolutely critical then just to try and counteract that. It is. That, along with proper nutrition, especially vitamin D supplementation, astronauts who really maintain higher intensity exercise often manage to keep their aerobic capacity pretty well. However, even with exercise, things like joint cartilage thinning and degeneration are still concerns, potentially leading to osteoarthritis down the line. It's just this fundamental fight against decay in an environment where your body feels like it doesn't need to support itself anymore.
What about our brains and senses? I can only imagine how disorienting just being up there must be.
Well, space motion sickness, or SMS, that's a very common acute risk, usually in the first few days, manifests as nausea, vomiting, imbalance. Pretty unpleasant. Microgravity messes with the vestibular system, the part of your inner ear that controls balance. It makes the brain misinterpret signals about where you are in space, which leads to changes in eye movement control, posture, even how you walk when you get back.
But what sounds truly fascinating, and maybe a bit unsettling, is the actual physical impact on the brain structure itself.
Indeed. Long-term spaceflight can literally cause your brain to shift inside your skull. We see increased fluid volume, cerebrospinal fluid around the brain. We see narrowing of certain brain structures, like the central sulcus, and even an actual upward displacement of the entire brain. Now, this can lead to increased intracranial pressure, and that can cause visual disturbances, headaches, and even carries a risk of intracerebral hemorrhage, a bleed in the brain. Astronauts also experience something called spaceflight-associated neuroocular syndrome, or SANS. It affects about two-thirds of ISS crew members, causes swelling of the optic disc, flattening of the eyeball, blurred vision. It's likely due to that fluid redistribution and the elevated pressures inside the skull. Imagine waking up one day with permanently blurry vision just from being in space.
So your vision actually changes. What about other senses? Does everything just feel different up there?
Yeah. Hearing can definitely deteriorate. Partly due to the chronic background noise, it's around 60–70 decibels on the ISS, kind of like a busy office, but constant. Plus vibrations and maybe even elevated carbon dioxide levels contribute. The sense of smell and taste can also be affected. Some researchers hypothesize this could contribute to what they call space anorexia, where astronauts lose appetite. Could be linked to the specific space diets and how the food is processed too. Even your sense of touch and temperature perception, cutaneous sensations, they change under simulated microgravity. You're constantly adapting to a truly alien sensory environment.
And then there's the cosmic radiation hazard from the Big Five. That sounds truly daunting, almost like something out of science fiction, but it's real.
It is very real, and it's a profound threat. It has much higher ionizing properties than the medical radiation we encounter on Earth. Just to put it in perspective, a 6-month stint on the ISS exposes an astronaut to about 50–100 millisieverts, or MSV. That's roughly equivalent to getting 53 head CT scans. Now, for a potential Mars mission, the estimate jumps to 870–1200 millisV. That's like getting 632 head CTs. Cosmic radiation significantly increases the risk of neurodegenerative diseases, premature aging, and malignant brain tumors. It causes genetic mutations, DNA damage, leading to higher rates of various cancers, particularly lung, breast, stomach, and colon. It also really impacts the immune system. We see thymus atrophy, reduced T-cell function, basically weakening your body's natural defenses.
And this has implications not just for the crew themselves, but potentially for future generations. The whole idea of having children conceived or developing in space.
Potentially, yes. Reproductive cells, sperm and eggs, are extremely susceptible to radiation damage. Studies in animals show impaired spore production, spermatogenesis, in males exposed to space-like radiation. And for women, estimates suggest a Mars trip could reduce their ovarian reserve by up to 50%. That could lead to premature menopause. Even embryos developing under simulated cosmic radiation show significant genetic damage and epigenetic changes, alterations in how genes are expressed. However, there is some innovative research. Scientists stored freeze-dried mouse sperm on the ISS for years, and when it was brought back and used for fertilization, it still produced healthy offspring. So that suggests possibilities for maybe long-term genetic preservation in space, but it highlights the huge biological hurdles for true deep space colonization.
So the biological challenges are just immense. How do astronauts cope with the psychological side? The strain of isolation, confinement? It can't just be physical.
Absolutely not. That's another critical area. Isolation is one of those big five hazards, remember. Astronauts face potential interpersonal conflicts, especially on long missions. Circadian rhythm disturbances are a big one. Imagine 16 sunrises and sunsets every 24 hours. That messes with your internal clock. Leads to sleep disorders, increased stress from the demanding workload. It often results in needing pharmacotherapy, medication, just to manage sleep issues. So, psychiatric screening before missions is crucial not just for astronauts, but even for future space tourists. They're even considering selecting candidates based on neurogenetic profiles, looking for genes that might indicate better adaptation to stress. Ultimately, the mental state of the crew is absolutely paramount for mission success. You know, a happy crew is generally a productive and safe crew.
Right. This brings us inevitably to the future. With all these mounting challenges, the aging hardware, the human toll, what are the plans for the ISS beyond 2030? It can't last forever, surely.
No, it can't. The current plan, the official strategy, is to continue operations through the year 2030. And then the idea is to transition to one or more commercially owned and operated space stations in low Earth orbit. NASA projects this transition could save them a significant amount of money, somewhere between $1.3 to $1.8 billion per year, basically by shifting from being the owner-operator to being potentially a customer of these commercial stations. It's worth remembering, the ISS was initially only set to retire back in 2015, so it's already had several life extensions. This next decade is really about a managed strategic handover.
And then comes the ultimate question. How do you safely bring down something so massive, the size of a football field, orbiting at 17,500 miles per hour, without risking an uncontrolled crash?
That is the challenge of the deorbit plan. The target is for 2031. The aim is to bring it down in a controlled manner into a very remote, unpopulated area of the South Pacific Ocean, often called Point Nemo. It's a spacecraft cemetery, basically. Now, the original plan relied solely on using 3 Russian Progress cargo spacecraft to push it down, but that was later deemed insufficient for a truly controlled deorbit, didn't offer enough precision or control. So the updated plan now includes a brand new, yet-to-be-developed U.S. deorbit vehicle. This would work together with 2 Russian Progress spacecraft. And SpaceX was actually awarded the contract $843 million back in June 2024 to build this crucial U.S. deorbit vehicle.
Wow, $843 million just for the deorbit vehicle. That's a huge undertaking on its own, especially involving international partners.
Yeah.
What are the biggest hurdles to actually executing this really complex deorbit plan on time?
Yeah, there are several significant challenges looming. Firstly, there's the Russian commitment. Russia is only formally committed to ISS operations through 2028 right now, not yet through the full 2030. Those negotiations for the extension, they're expected sometime in 2025, 2026. Without their full commitment through 2030 and for the deorbit itself, the whole controlled deorbit plan becomes, well, uncertain. Secondly, that U.S. deorbit vehicle, it faces major funding and schedule risks. The government's own cost estimate for it rose to $1.5 billion. And the development schedule, they're aiming for roughly 5.5 years from the contract award to a 2029 launch. That's considered pretty unrealistic, frankly, compared to the average of about 8.5 years for major NASA development programs.
So there's a very real chance of delay then, or maybe even a completely different outcome than what's currently planned.
Absolutely. If those commercial LEO destinations aren't ready in time, or if that U.S. deorbit vehicle gets delayed past 2029, NASA might find itself needing to extend ISS operations beyond 2030, which of course brings increased risks and costs, operating a station that's already showing significant signs of age. There has been some talk. One proposed mitigation is just to keep the ISS crewed and operating indefinitely, but that obviously introduces its own whole host of operational, financial, and frankly, human factor challenges we've just discussed.
But presumably there are contingency plans, just in case an emergency deorbit becomes necessary before 2031.
Yes, thankfully. NASA and Roscosmos do have a revised contingency deorbit plan that was put in place in September 2023. And the specific roles and responsibilities for that contingency were agreed upon just recently in July 2024. This plan outlines how they would manage an emergency deorbit if needed before the big planned one. It relies on both agencies' assets, spacecraft, ground control for altitude, and attitude control, ensuring they can work together effectively if the worst should happen.
So as we've explored today, the International Space Station, it really is this incredible testament to human ingenuity, to international cooperation. It's provided invaluable insights into everything from, cancer treatments right down here on Earth, to how our very bodies adapt or maladapt to space. Yet its future is clearly filled with both incredible potential and some really complex challenges. From that aging hardware and the cosmic rays literally changing our biology to the intricate dance of international politics and these ambitious, risky deorbit plans, it truly makes you wonder about that delicate balance, doesn't it? Between our innate drive to explore and the very real, sometimes profound risks we uncover along the way.
It absolutely does. And it highlights that space exploration isn't just about building bigger rockets and fancier satellites. It's fundamentally about understanding human limits, physical and psychological. It's about managing unprecedented complex risks. And it's about the sheer long-term commitment required to sustain any human presence beyond Earth. The ISS has taught us so much already, and the lessons we're still learning from its continued operation and eventually its retirement. Those lessons will be absolutely crucial for the next chapters of human spaceflight, whether that's returning to the moon, heading to Mars, or even going beyond. You could say the very future of humanity in space really depends on how well we learn these lessons now.
If you like and want to hear more of these discussions, please like this video and subscribe to our channel. Thank you for listening, and we'll see you on the next episode of Built Through Time.